It's here we are, heading into a long weekend. You can see the effect on the attendance. We are going to talk today about adaptive quadrature and then about Gaussian quadrature. So all of these things are about how to best find the value of an integral. This is a significant problem in the sense that finding the values of integrals are almost always done numerically. Solving of differential equations are almost always done numerically. I understand that when you take Math 152 or you take Math 260, what you learn how to find exact solutions you need, and there's validity to this. But the reality of the situation is when you get complicated systems, you get complicated solutions, and you don't have these nice closed form solutions. And the numerical methods are how a lot of the numbers are gotten from the definite integrals or the solutions to differential equations. So this is a significant issue in a numerical analysis. Okay, so what we have done is looked at some of the basic methods, the Newton-Cotes method, the open and closed ones. And then now we've identified that we actually have not too bad with the composite rules, the composite Simpson's rule, for example. It actually works quite well. We can get down to machine epsilon, typically speaking, but we realized that we have to do a lot of function evaluations, like really a lot. So it can take up quite a lot of time. So now we're looking at things to do to improve upon that. And our first idea is to not have equally spaced nodes. Okay, so this is ruled out if you have, for some reason, for data collection methods, if you for some reason have a fixed set of nodes for something, then you're done. You can't use adaptive quadrature. If you're allowed to pick your node position, then what we're going to do is move the nodes around so that more nodes are being used where the function is changing more quickly and less are used where it is not. That's the idea. That's where we were at last time. And we want to place the nodes efficiently so that we get the least number of function evaluations. And it also has to be done automatically. You can't have somebody sort of watching the procedure going, oh, I see what you should do. Look, the function's changing over here. Move the nodes over there. That can't happen. We need it to be happening in some sort of automatic method. So that's what we're going to take a look at today. So we've got we're going to do this based on the Simpson's rule. So let's just take a look at the formula for the Simpson's rule. That would be if we were trying on this is a non-composite form, one polynomial for the entire interval from A to B. So this is what it looks like. This is Simpson's rule. It looks like, well, this is kind of a funny way of writing it, but it's the Simpson's rule on the interval AB minus h to the 5 over 90 times the fourth derivative evaluated at some psi where psi is in AB. Okay, that's the Simpson's rule. This is our method. That is where we use a quadratic polynomial. And then we have that guy there. The actual rule, it looks like this, h over 3. So we evaluate the function at A. We evaluate the function at A plus h. That's in the middle. And we evaluate the function at B. That's the Simpson rule thing. We've got that 4 there. We went through the derivation of this. Okay. We have 3 for the non-composite Simpson rule. We have 3 function evaluations, and we combine the values in this manner, and we get this estimate. So what we're now going to try to do is understand, should we further subdivide the interval? And if the answer to that question is yes, we're going to ask, how should we subdivide the interval? Okay, so we're started here, and we've got the function like that between A and B. And we've got these 3 things like that. And we've made an estimate of the area under the curve. Now we're asked, should we further subdivide? And if so, should we divide it like that? Or should we divide like, who knows? What should we do? Where should we put further, so that's what we're asking ourselves. Okay, so we don't actually know, we don't know this guy like usual. So we don't know, how large the error is. So what we're gonna do is estimate the error by applying the composite Simpson rule. Let's see how this works out. Okay, so here's gonna be, now I'm gonna have, 4 intervals. Okay, so what we're gonna do then is, this is gonna be our, gonna go like this, that will look like this. This is the Simpson rule. N is 4. We have 4 times A plus H over 2. 2 times that's A plus, that's the one in the middle, and then 4. That's 2H, that's 2H over 4, 3H over 4. Okay, and then the last one. Okay, there. And we have the error associated with this one here. H over 2 to the 4, B minus A over 180, F to the 4 at mu, and mu is somewhere in there. Okay. Now, we've done these 2 things, and we're gonna make an assumption. We're gonna make an assumption that, and I'm gonna use, okay, here, I just wanna, I try not to introduce too much confusion, but I also don't want to keep writing the same thing out over and over again. So we'll notice this notation right here. This means this, okay? That is the Simpson rule evaluated on the interval AB. Okay, so I'm gonna use that notation so that we can write things more succinctly. So this is then going to be like this. This is the Simpson rule on A to A plus B over 2, plus the Simpson rule on A plus B over 2 to B, minus 1/16 times H 5 over 90, 4. We'll just note this guy up here, here as equation 1, and this guy here as equation 2. Okay. Now, I'm going to make an assumption. I'm going to assume that F for psi is approximately the same as F for mu. Okay, if the if the situation is thus, if the fourth derivative is continuous, you don't actually know that, but if that's the case, that will first, this will be true. This will be true for sufficiently small a. Okay, so there's a couple of assumptions built in here. That is, I've got small interval, and I've got a function whose fourth derivative is continuous. So that then when that happens, I'm going to equate 1 and 2. They're both an estimate of the integral. So I'm going to just equate the 2 of them and see what I get. I get that SAB minus H to the 5 over 90 times the fourth derivative psi is approximately equal to this guy here. I mean, I just did 2 estimates on the integral, and I'm trying to say that they should be approximately equal under certain conditions. That's what I have. Okay, I'm waiting one. This is the point of doing this. Now, these two things have been assumed to be equal. That's why there's no mu anymore. I've made this assumption right here. And so I replaced as for derivative of the function that mu or derivative of the function dot. I put these two things. This gives me an estimate of this guy here. I'm solving for this. F equal to 16 over 15, S A B minus S A 2. So I've done two one time with for the whole interval and one time for the two intervals. That gives us fourth. Oh yes, thank you. Got the four there. Thank you. Definitely fourth derivative there. Okay, so that allows us then to get a known error estimate for how badly our function differs. This is how badly does our function differ from the Simpson estimate, and that then can be stated in terms of the Simpson estimates themselves. I do not need to. Now I've eliminated this guy right here. Okay, so this is an effort to get a sense of how much error I actually have. Okay, I noticed this number here of 115. And then you're going to notice that magically this changes to 110. That's just to allow a little bit of a margin. We're making some assumptions here that those two derivatives are equal, et cetera, et cetera. So that is a caution. So this is it's just changing to be not taking exactly what I've calculated, but actually just releasing the tolerance a little bit. Okay, so what we do with this adaptive quadrature based on the Simpsons rule, we do two of them, and then we check is the difference between the two of them less than some tolerance which we pick. You pick some tolerance. I don't know. Here it says predefined tolerance epsilon. This would be equal to epsilon. So we check that. And then we decide whether we should continue in that area or not, adding more nodes in that area. Okay, so that allows us to stop on one half. Okay, so what we're doing is we take the Simpsons rule across the whole thing, and then we take the Simpson rule in two pieces, and then we ask, have we come within our tolerance here, and have we come within our tolerance here? The difference between it, if we have, say we came within our tolerance here, we're pretty happy with this, then, but we didn't here, then we would add here and we would do it again. And we're like, did we come within our tolerance on these two pieces? And if we perhaps came within the tolerance on this one, then we would say, okay, fine, stop doing that and then add the next node here. This is a way of automatically placing the node by observing what kind of errors we're inserting, and then when we go below the desired amount of error in one piece, we stop doing any more calculations on that piece, and we continue adding to the area where we don't have what we want. Okay, so let's just make a note of this 110 rather than 115, since we assume so we're being conservative here. So basically, good idea to be conservative in error estimates. Okay. Now, if we're within the tolerance, then this guy, these two Simpson method things, so one on the first half and one on the second half are approximations. If we're not within the tolerance, then we apply the same procedure separately on the two subintervals. And we set the tolerance of each subinterval to be half. When an overall error of epsilon, so we're like, okay, we'll allow us to have epsilon over 2 error in each half. And we then see whether we've got this is a recursive procedure. So now we go ahead and we apply, well, I've already drawn the diagram. We apply it, if we're not below epsilon over 2 on the two things, then we say, okay, if we're not, then let's do it, divide in half and do it again. And we'll have to be within epsilon of 4. And this allows the nodes to move to where they're moving. Okay. Let's just have a look at what this looks like. So adaptive quadrature is used basically in all of the built-in numerical integration routine. So here's a function, 100 over x squared, and sine 10x. Let me just say something about what that. I think the quad function is no longer well used, but that's not that quad function. This uses actually adaptive Simpson, and then the MATLAB, which is the newer flavor of doing this, the integral command, which uses which we're not handling actually. This uses global adaptive quadrature. So we just did this guy here. It's a little bit simpler and it's also slightly unpaid. Okay, so we've got this function here. It's a sharp peak near x equals 1, but it's also flat over much of its range. Okay, so what happens when you apply Simpson's rule with the adaptive quadrature? This is how it plays together. You start going with your first node. That's going to be well, it's hard to see here, but you're basically going to be somewhere here, here, and here. And then you're not below your tolerance, then you place a node here and here, and then actually after, and then maybe then it's going to be here, 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 and here, like that. And then again, you're going in half here, 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 roughly it looks like a node here, like that. Each time you're going in half, and at that point, right here on the thing, your area calculation is within the given tolerance. So you stop with that part of the program, and then you go here, here, going in half here and here, however that looks, and here, 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 like that. And as soon as you get where you want to be, you stop. And so the point is that you're using more nodes. You're using more nodes basically where the function is changing quickly, and all you've got is here in place that controls it to the manual, so it can automatically right now. That's adaptive quadrature. Move the node. Anybody got questions, comments about this one? Let's take a look now at a method, a precise method of. So this is a I don't know how you call it, heuristic method, but it is a method of not how we would have it's relying on a computational procedure to decide how to place your nodes. We're going to take another look at where to place the nodes optimally. This is not based on doing calculations. This is based on figuring out what to do from a theoretical standpoint. So here's the first one we're going to see like this is Gaussian quadrature. Okay, let us just let us just review, where we're at. So we have seen the Newton-Cotes formula. Those were with equally spaced nodes. So those ones were the open one, which was the midpoint. That was an open Newton-Cotes formula because we didn't use the endpoint, we just used the midpoint. And then the closed ones that we've seen, the trapezoidal version, we saw that one and we saw Simpson. Okay, we've just been talking about that. Okay, those are the closed Newton-Cotes. What was the problem? The closed method. What's the problem, especially if it's not a composite one? Problem. I happened to look at you, sorry. So the answer here was it doesn't take into account the shape of the function. So if I'm going to use the non-composite trapezoidal and or Simpson's rule, and I'm in fact thinking of doing this, I've got my function, and then I'm going to use the trapezoidal rule, and then I want to do better than that. So I use Simpson's rule, I put a quadratic. Now what would I possibly do next? And I interpolated with a linear interpolant, then I did it with a quadratic, a 2-point, 3-point interpolant, then what would I do? Yeah, exactly, and what would be the problem? Yeah, so I mean, the only way to do it here is I need a higher order polynomial for more accuracy, quote unquote, for more accuracy. And that leads to the Runge's phenomena, and then we don't get more accuracy. That was step one. Then we said, okay, fine. So we're not happy with that. We'll do the composite version, where we divide our function up into a whole bunch of intervals like that, and we'll use a different quadratic in each interval, like that. That way we can keep the value of the and those are also at equally spaced nodes. So the problems there, we have lower order accuracy. So we had well, the trapezoidal composite one were like that, or OH squared, like that. So there's that problem. And we had large numbers of computations. Like we had to really make a lot of intervals. Make lots of computations. Okay. So what have we done? We have already looked at nodes, except for previous our last little lecture or last little section where we said, okay, fine, let us just move the nodes around as a result, the adaptive model. Now we're going to look at choosing the nodes in advance to give us higher order nodes. So they'll be like OH5 or OH8 or something like that. And it'll be better for accuracy purposes. And we also will hopefully find something that's quite robust. So let's just back up a little bit and we're talking, what is the form of a quadratic rule? What do they all look like? I mean, they all look the same. And that is we are trying to integrate a function over an interval, and we're turning it into a sum. And we have two things that we can do. We can choose these little weights, like whatever we multiply by, and we can choose. So we can choose those weights, and we can choose where to evaluate the function at. Right, that's it, right? That's what they all look like. There's something times f at something, but something else times f at something else. That's the whole question. So we can, if we know the underlying function, or where we have the ability to measure data where we want, then we can choose both the positioning of the node and how much emphasis we're gonna put on each one of the nodes. So let's just here, just write out the most basic, trapezoidal rule. What does it look like? F at A plus 2 times F at A plus B over 2, right? No, hang on. What does it look like? Hang on, I'm going to get it right. Here is A, and here is B. We're going like that, going like that. So we're taking 1/2 of F at A plus F at B. Right? That's the basic model on the Simpson. So what we're doing is this would be X1 in this new model X2, and then the weights here, this would be C1 and C2. Right? But all the function periods look like this. There's some amount of this function evaluation plus some amount of this function evaluation, and maybe some amount of some other function evaluation. Do what you want, right? This is the most general case. Okay. Okay, so we are going to have n function evaluation, and each function evaluation is going to have an associated choosable weight with it. How many degrees of freedom do I have? Pardon? 2n, absolutely, right? Okay, let's just maybe write this out so we can for sure see that. This looks like this. C1f at x1 plus C2f at x2 plus dot plus Cnf at xn. And I get to pick this, and I get to pick this. Get to pick this, and I get to pick this. I have 2 n's in about 2. Okay, we did mention earlier that a quadrature rule has degree d if it is exact for all polynomials of at most of the degree at most d. Okay, so what we're going to try to do is choose the node and choose the constant so that our quadrature rule, this guy right here, this one, that quadrature rule has degree 2n minus 1. So that's our ideal version. Okay, we're going to do a simple example and see how this works. We're going to start with the symmetric interval, -1, 1. And we're going to start with the case where we are having 2 function evaluations. So we're considering, and we have a function, we want to integrate it from -1 to 1. Okay, there it is. And we are going to be allowed to evaluate the function at 2 different places. So it's going to be approximate, we're going to make this thing approximately equal to some weight times the function at x1 plus some other weight times the function at x2. Okay, that's how I'm going to evaluate it. Maybe it may be instructive just to imagine this. What if we were going like this, -1 to 1, like this, x squared log x dx. Okay, imagine us doing that. And then I can say, okay, fine, you can pick some number, 2. And you can then evaluate this function at some number, let's just say, maybe I pick -1/2. This would be then -1/2 squared. That's not going to work well. Let's put log of absolute value of x. -1/2 squared times log of 1/2. And then I'm allowed to pick some other number. I'm just going to pick it, 3, and I'm going to evaluate maybe at, I don't know, 3/4. This is just a simple example to sort of show you what's happening. I was allowed to choose this -1/2. I was allowed to choose this 3/4. I chose the 3 and I chose the 2. I made 4 choices. Okay. Now I'm trying to use 4 choices. It's going to give you the best result. Lots of different choices we can make. Which four choices will result in the closest approximation to the actual value? That is actually not such an easy problem in the general sense. But let's see how we can at least get traction on it when we have the simplest example, function evaluation over this symmetric interval. Okay. What we're going to do is we're going to figure out these guys, the four choices we're allowed to make. We're going to figure those out so that the above equation, this guy here, the above equation is exact when my function equals these four things. So I'm thinking about this function here. So when f of x is equal to 1, I want my rule to work out exact. Okay, when my function is f of x equals x, I want my quadrature rule to be exact. And I have four of them because I have four things I can choose. So I can choose those four things to force these four functions to be exact using this quadrature rule. Then, by the linearity of this situation, I'm going to say more about that. If I make it exact for these monomials, then this quadrature rule will be exact for all polynomials up to degree 3. Okay, because a polynomial like this guy, there's a polynomial. Why don't we even make it a degree 3? Okay, there's a polynomial of degree 3. That polynomial, I could be thinking of it like this. It's a vector, 3, 0, 0, minus 4. Right? 3 times x squared plus no times x squared plus no times x minus 4. Right? We recall that these guys are basis vectors for the vector space of polynomials. Okay. Let's leave that perhaps and go here and we'll come back to it. So what do I want? I'm going to take the function f of x equals to 1. And I want that the integral from -1 to 1 of 1 dx, now that's my f of x, is going to be equal to some c1 times f at x1 plus some c2 times f at x2. And what is that integral from -1 to 1 of 1? So exactly what is this integral? 2. It's 2, right? So it means I want 2 to be equal to c1. And then what is f at x1? No, 1. The whole function is 1 at all values of x, right? Okay, so f at x1 is 1 and f at x2 is 2. Okay, so that means if I want this quadrature rule to work for function f of x equals 1, it must be the case that c1 plus c2 is equal to 2. Okay, I mean f of x1 is equal to f at x2 is equal to 1 because the whole function is just 1. Constant. I'll do the same thing now. I'm going to consider the function f of x equals x. These are the monomial basis vectors that I'm looking at. I'm saying then that the integral, the -1 to 1, the integral from -1 to 1 of x dx is going to be equal to c1. What is f of x1? Pardon? Yes, it's x, but x what? x1, right? It's the actual value x1, right? F of x equals x, so f of x1 equals x1. And then this guy is x2. That is f of x2. And what is the integral from -1 to 1 of x dx? 0. That's 0, right? You know what this is. That means that's telling me that 0 has to be equal to C1 x1 plus C2 x2. Equation number 2. Keep going. F at x equals to x squared. I'm going to take the integral from -1 to 1 of x squared dx. I'm going to say that has got to be equal to C1 times x1 squared plus C2 times x2 squared. And that has got to be equal to what? What is the integral from -1 to 1 of x squared? Two-thirds. I like two-thirds better than that. Two-thirds. Okay, that tells me that two-thirds has got to be equal to this. C1 x1 squared plus C2 x2 squared. Okay, I'll keep going. I got, now we're going to do the one here for f of x equals x cubed. I'm going to do the same thing. -1 to 1 of x cubed dx equals C1 x1 cubed plus C2 x2 cubed. And that is equal to what? 0. It's an odd function over a symmetric interval. 0 is equal to C1 x1 cubed plus C2 x1 x2. Okay. Look at this nice happy situation. 4 equations, 4 unknowns. They're not all linear, makes it a little bit harder to solve, but this is not difficult, especially since we've got these nice zeros, right? So you go ahead and do this, solve the system, and you find out C1 is 1, C2 is 2, and X1 is -1/3, and X2 is 3. X1 is -1 over root 3, and X2 is -1 over root 3. And therefore, you conclude, therefore you conclude that your best case scenario, your 2-point Gaussian quadrature rule is this, right here. You should always be able to do this for a 2-point rule or a 3-point rule. Like you can just say to yourself, what if I say it's a 3-point rule? Then it's going to look like this. There. Now it's a 3-point rule. I'll try to make it exact for f of x equals 1, x squared, x cubed, and x to the 4th. I'll make it exact for those ones, and then I'll just use it for everything else. I have that degree of precision, 2n -1. Okay, here I would have 6 equations and 6 unknowns. Pardon? Oh yeah, 6. X to the 5. What did I say? Accidentally? So this is degrees of freedom. Degree of freedom is equal to 6. Yeah. So we would have this will be exact. Degree 5. Okay, so that is we've got 3, and then 3 times 2. We've got 3 things here, and we've got 3 times 2 is 6, and then 6 minus 1 is 5. Okay, so that means that if I was to correctly figure these things out is by the method that I just said, this quadrature rule that I just invented would be exact for all polynomials that look like this. Degree 5. The 5 plus cx to the 4 plus cx cubed plus dx squared plus dx plus f. Those guys, I employed this rule, so whatever is directed capitals and the whatever is directed weight, it's going to be exactly the right answer. And then I'll just start using it for other stuff. It's not a polynomial. Now, of course, I'm going to get some error, but I've selected the maximally precise position. Okay, now as you can see from the example is that we went through on the most basic 2.1 and we found that we had to get four equations and four unknowns that we had to solve, and they're nonlinear. So it's kind of tedious to go through this each time. Okay, but for sure this is the 2 point rule here. Okay, so now what happens is the theory goes into a place to look for these models based on what are called the solving points. So the question is, sometimes when you can't solve a differential equation, one method of doing that is using the power solution, and then you get an infinite series in that case, and then you just truncate the A close enough, right? Pardon me? This is not a power, we're not looking at this is not a power series. What we're doing is we're saying we are taking a finite number of points that we're going to evaluate our function at, and then we will weight them optimally, and we will optimum means getting the maximum degree polynomial that is exact for. And then why do we think the polynomial? And so what we're doing is we're thinking maybe around like, well, what we do is just very much function. We integrate it with someone. And so we're really excited about that. Because we already learned from before, we can take whatever function we want and incorporate it as a polynomial and factors in. We have the Weierstrass, what was the other guy was, the name of my head. There's another guy who did the both, and I can't remember. Anyway, there's a theorem by Weierstrass, like any continuous function can be approximated with as much accuracy as you want by a polynomial. So it's an important theorem, right, to say that no matter what continuous function you have, there's some polynomial that will go through that thing really nicely. Okay, so now we're moving along here, and we are going to introduce the idea, perhaps, or perhaps maybe you are already familiar with this idea of orthogonal polynomial. Okay, first of all, let's make clear, what does this word mean, orthogonal? Pardon? Well, it's true that if two vectors are orthogonal, they're linearly independent, but that's not what orthogonal means. Yeah, so this means at right angles, and typically speaking, in Math 232, for example, you would realize that would mean that the dot product was 0. Right? We have two vectors, their dot product is 0. We realize the vectors are orthogonal to one another. Let us remind ourselves of that fact. Let us imagine I had a vector right here on 1, then I have another vector here on -1, 1. Okay, those two vectors are at right angles to one another. And let's look at what we would do here. We have B1 and B2. We would look at the dot product, B1 dot B2, like that, and it looks like this, B1 dot B2, like that. It looks like this, 1 times -1 plus 1 times 1, that has to be 0. At which point we conclude that the two vectors are orthogonal. But look at what we're doing here. We are basically doing some sort of multiplication of components and then adding them. Right? This is the happy dot product situation. Okay, so what we're thinking here is the same thing. We are thinking multiplying polynomials and somehow adding them, and the result is come out to 0. What does that look like? Okay, That is what we just have to clarify. It's just an enlargement of the same idea. Let me just write a couple of things. What are orthogonal polynomials? We have to understand what this is. It's a family of polynomials. Such that any two different polynomials from the family are orthogonal to one another. Under some inner product. Okay. Okay, you now maybe think to yourself, oh no, I might have heard that word before, but we didn't really touch on it too deeply, and that's probably true, depending on exactly what your first study has been. But the inner product, the dot product is an example. So we in Math 232, we actually vaguely talked about inner and outer product, and we ditched the outer product completely right away. I forgot that doesn't really matter. And then, but then we have this idea of an inner product, and for vector spaces, which are Rn, the inner product, we have that as a dot product. That is just an example of an inner product. So now we're going to have possibly a different type of inner product, but it functions in the same manner and it tells you the same thing as the dot product, which is also an inner product. Okay, so in this case, the inner product is what we're looking what we're getting at is we'll have a particular definite integral of the product of two polynomials is 0. Okay, so it's the same idea. I'll put that back in a sec. It's the same idea. We have this vector idea. Now what we're going to have is we're going to have one polynomial, something. We're going to have a second polynomial, something. We're going to multiply them together and add, and the result is going to be 0. Of course, we can't do it quite as easily like that, but what we're going to do is we're going to take some integral of P1 times P2, like that, multiply them together, and add, and we're going to do this sum now instead of this sum, and we're going to get to it. We're going to go through those people. Okay, let's see. Let's see what we can say about this. The first class of these guys we're going to look at. So you should, I mean, if I was you, I think actually orthogonal polynomials is a really interesting topic. There's a huge amount of theory behind this and lots of important results. You can just go orthogonal polynomials like that into Wikipedia. You know how you can always read like the first paragraph and then you get that. At least you can learn something, right? Then so you could check that out. Okay, so there are different families of orthogonal polynomials, and they are sometimes named after somebody who figured out the property. So first ones we're going to take a look at here are the Legendre polynomials, and they are polynomials with these properties. The nth degree polynomial is monic, which means that the coefficient on the highest order term is 1. So they all look like this. The something of x is something x to the largest power, and that something is always 1. That's what it means to be monic. And when we integrate from -1 to 1, we always get 0 whenever we have this polynomial less than or equal to the degree of x. Let me just, before we break, let me just give you an example. Here is a polynomial of degree 1. There it is. Here is a Legendre polynomial, C2. Now watch this. Someone's gonna get hurt when you hear that. Okay, watch this. We got that. We're gonna take any polynomial of degree less than or equal to 2. That would be this one, for example. We are gonna multiply by this magic polynomial here. One of the Legendre polynomials. We're gonna do it over the interval from -1 to 1, and this will be 0, regardless of the value. It is not a coincidence that -1 over √3 and +1 over √3 from the previous example happens to be the roots of this polynomial. Okay. All right. I am going to stop right there because we are out of time, and we will continue with an extremely exciting situation right on Monday. I have posted the last 2 computing assignments. Both of them are sitting there. Have a look, and you've got 2 weeks till the next one is a little bit under 2 weeks, but 2 weeks to go till the next one. Have a good long weekend.